Hey everyone, Josh Patterson, Director of AI Infrastructure, and I'm here today to talk about RAPIDS. So RAPIDS is our end-to-end accelerated GPU data science set of libraries and tools, really to help people go from data prep to training to visualization. But before I jump into the library, I first want to kind of talk about the motivation for why we built this. So I'm going to start with really our foundation, which is built on Apache Arrow. So when I first joined NVIDIA, I'm the director of AI infrastructure, and so we've been building out different pipelines to help out different teams. And one of the things I wanted to do was, based on some of my cyber background, is connect a really fast in-memory GPU database, at the time MapD, now OmniSci, directly to something called Graphistry, a graph visualization engine. And so OmniSci can do these really, really fast OLAP type queries. It's a SQL in GPU memory database. And Graphistry can visualize millions of nodes and tens of millions of edges. And it's just this really smooth graph visualization tool, just orders of magnitude faster than things like Gephi. But going from one to the other took about 2 minutes, mainly because we had to copy data back to host, and then we had to convert it to another format, then we would copy it back to the GPU, and then we would do something with it. And that latency in between was just kind of unacceptable. So our goal was to remove that latency, have everything that's on the GPU be able to talk to everything else that's already on the GPU. At the same time, there was the Apache Arrow movement. Show of hands if you know about Apache Arrow. OK, so most of the room now, which is every time I give this talk, the hands go up more and more. So Apache Arrow is just a columnar representation of data that's in memory that can be used across languages and also across hardware. So it has Java, C, C++, R, Julia, Rust, Go, I believe Swift now, interfaces and bindings. And we also can do it on the GPU side with the CUDA C++ API. And so given that Apache Arrow was kind of becoming ubiquitous in big data, about 2 years ago, we decided to standardize around Apache Arrow as well for GPU applications, so we could pass data back and forth between them without having to serialize and deserialize data, essentially waste computational resources. And so the top half of this slide is actually from a Spark talk about why Spark is faster than MapReduce. And what we've done with RAPIDS really is just take that exact same idea and just moved it to GPU memory. So instead of like traditional GPU processing, where I have everything in host memory and I do a lot of things on the host side, and then I move it to the GPU, do something really computationally quote unquote intensive, and then move it back, what if we just did all of the computation on the GPU? And I know what you're saying. You're NVIDIA. Obviously, you want to sell more GPUs and you want to push more computation there. Mem copies are actually the bane of data science. Moving data is just a huge problem. So what we actually realized very quickly, even things that weren't computationally demanding, just doing a unary or binary operation, just doing some type of scan or filter, because the GPU memory is an order of magnitude faster, because we have more just pure cores, all these things get these massive accelerations. And so as long as you're not moving the data, the whole end-to-end pipeline is actually a lot faster. And so we can start doing now traditional data science. And that's really what RAPIDS is, and that's the motivation for it. So RAPIDS is a collection of libraries. And before I talk about those libraries, I want to talk about how we designed the API. And so I had the privilege of hearing Francois talk at AnacondaCon about speed, UX, and iteration, and how that's winning Kaggle. And really the best data scientist in the world is not about being the smartest. It's about iterating faster. And if you have tools that have a good user experience and they're fast, relatively fast, you will eventually win any competition. You'll be the best data scientist because you can iterate. Iteration is really the key. So when we built RAPIDS, we said, OK, what are the best APIs? What are the most user-friendly languages? What are the best intuitive ways of exposing how to do a process without asking people to learn something new? And obviously, we gravitated to the Python ecosystem. Pandas, Scikit-Learn, NetworkX, they all have massive adoption. And so the Cu data frame, the Cu machine learning, cuGraph, which we just call cuDF, cuML, and cuGraph for short, That's what they're all about. It's literally these same APIs. And when we first started, the cuDF API might have been like 90% compatible with Pandas. What we've learned over time is the more you make something Pythonic, the more interoperability you get with other libraries. So when we want to start integrating with things like Bokeh or with Dask or with other tools, we realized just modifying our API to make it even more Pandas-like gives us a lot more functionality really, really quickly. And so they're getting closer and closer every release to being drop-in replacements. On the cuML side, it's about as close to a drop-in replacement as you can possibly make it. cuGraph is the next closest, and cuDF is, as I said, it's probably 90–95% the same API, and we're continuing to make it closer and closer so we can get more interoperability with other frameworks. And so when we launched RAPIDS about 6–7 months ago in Munich in October, this was kind of Jensen's favorite little doodle that one of our UX leads did around how people spend their time. Traditionally, people are, they fire off some type of job, they go get some coffee, they talk with their cube mates, they realize they didn't do something they wanted to, they fire off another job, they wait. With RAPIDS, you get this kind of iterative approach where you don't really have a lot of time to wait for things because everything happens pretty quickly. So I'll talk a little bit more about cuDF. It's the backbone of RAPIDS, really. On one side, you have your low-level CUDA implementation, libcuDF. So it's pure CUDA C++. It does all the standard things, joins, group bys, filters. We're adding window functions in the 0.8 release. And then we add Python bindings. In the past, this used to be CFFI. We've switched all of it to Python in the latest release. And so this is where we expose this kind of proper Pandas-like API. We also use Numba for JIT compilation of user-defined functions. And then I'll talk more about how we scale this with Dask. And speaking of that, Dask. This is how we scale cuDF, cuML, and cuGraph. And so why Dask? A lot of people use a lot of other tools for big data processing. There are many out there. But one of the great things about Dask is it's Python native. It's been around for a very long time. It was kind of born from some of the HPC use cases around earth sciences, some really computationally demanding NumPy-like workflows. And what we really loved about it was the flexibility between data frames, arrays, machine learning, and it just kind of worked. You just kind of plugged in cuDF, and we got things out of the gate. We realized there were some things that didn't work, so we modified cuDF to be more Pandas-like, and then we get more functionality. So instead of building a whole new orchestration scheduling layer, we just take something like Dask and just add different computation. And because Dask is a lightweight scheduler, it just points to the GPU, and we're pretty happy. As I said earlier, it started in HPC, so it can be deployed with things like Slurm. It also is cloud native, so it has Kubernetes support. And on your exact same Hadoop Spark cluster, you can deploy Dask on Yarn.
Do you have any of this applicable for ETL for like Oracle-based databases by any chance?
So not for the database itself, but if you can just export the data, we can ingest any format that it would send. So CSV, some type of JSON. If you want to write it to disk first, and then you can just pull it in. So think of it pretty much how Oracle and Spark would work together. Oracle and Dask can work the same way because they have all the same connectors. And so in our next release, and then the release after that, continuing to make cuDF more Pandas-like. One of the really exciting things is replacing Dask's communication layer with something called OpenUCX. And this is really where HPC, high performance computing, and big data are really starting to smash together. So on the HPC side, MPI is kind of king. Everyone uses MPI. MPI gives you this very low latency, fast method of moving data around, which is just not really useful on the big data side when you're CPU bound. And so there have been a lot of things where, for instance, Mellanox has done all this RDMA with Spark, and while they've increased sorting by maybe 2x, the end-to-end workflows didn't really change because you gave all this horsepower to the communication layer, but nothing changed on the data processing layer. Well, the good thing is, with Dask, it runs on GPUs, and so we need things like RDMA. I want to be able to go from a GPU in this machine to a GPU in another machine and to shuffle data around. And now I can do this at 100 gigabits per second. with GPU direct memory access. And we can also use things like NVSwitch and NVLink to do this intranode as well. And so we're already seeing about a 20x performance increase versus using Pickle to going to something like UCX with RDMA. And what this really just boils down to is think about things like joins, where I want to join a group of data to a smaller group of data, and I don't really know where these joins are going to match up, and I need to shuffle data around. Having this remote direct memory access, this RDMA, is really important, and it was already basically built. And that's really the great thing about HPC. They've had these needs for these things for a very long time, and because Dask is very modular, we just added Python bindings to UCX, and then in 0.8, we'll be releasing our first kind of UCX integration to Dask, just another simple conda install. And you'll get a pretty massive improvement to ETL. We're also focusing on better error handling. This was one of the reasons why we removed all the CFFI and moved to Python, so we can pass these errors more cleanly to end users. And then just better memory monitoring and improved string support. And speaking of strings, in 0.6, our last release about a month ago, we open sourced our strings so we can now have power support. Most of our string operations are somewhere between 200 to 300x faster than Pandas, mainly because they're vectorized, they're running on the GPU. And we're continuing to add more string support, more regex support, and that's just going to continue to improve throughout the releases. And also, this will allow us to write data formats as well. So instead of copying data back to host and then writing it to CSV or Parquet or something else, we can directly write files from the GPU to disk. And the better string support also allows us to ingest data faster. So our CSV reader is somewhere between 12 to 20 times faster than your best CSV readers out there. In fact, one of the things I really love is CSVs in the Python ecosystem are really fast because there was this kind of arms race of who could have the best CSV reader. And then moving that to the GPU, we're getting some pretty amazing speed ups just out of the gate. There's some other things that we can do in the future to make that even faster. But for most people, I think the 20x cap is pretty good. We have some early customers who are not using any other part of RAPIDS except the CSV reader. Being able to use the GPU to read a CSV 20 times faster, then write it back to memory, and then pull it back into TensorFlow is solving so many of their I/O problems that's just worth the price of the GPU alone, which is kind of funny to me. But I didn't realize that some of the I/O problems were so painful. And so we continue down this path once we realize how much people enjoy the CSV reader. We have a Parquet and Orc reader coming out in this release. In the next release, we're going to have JSON, lines, and Avro. And we're going to continue to add more and more different data format support. And ETL is not just data frames. And so while RAPIDS focuses on the tabular part of traditional data science, we want to have clean hooks into deep learning. And so quick show of hands. Do you think there are more or less than 12 Python CUDA array libraries in the world today? So show of hands for people who think there's less than 12. Show of hands for people who think there's more than 12. OK, so obviously you guys know this. So there's about 15 CUDA Python array libraries. ArrayFire, Boreum, CuPy, TensorFlow has their own, PyCUDA, Numba, PyTorch. The list goes on. There's a lot of Python CUDA array libraries. We just thought it would be robbery to waste our engineering time to build yet another Python array library, when really everyone just wants NumPy on the GPU, but no one can really agree what NumPy on the GPU looks like. Probably because no one really agreed on what NumPy was early on until those two worlds kind of smashed together. And so instead of us trying to pick a winner or pick a favorite, we just said, what if we had interoperability with all of them? And so this is what we do with DLPack and the CUDA array interface. So with DLPack, I can basically just convert my columnar representation of data into another Python array format without ever leaving the GPU, without doing any type of conversion. And so we can go bidirectionally to PyTorch, Numba, CuPy, and Chainer. The CuPy is just the array side, Chainer is the deep learning framework, as well as MXNet. And what this allows us to do is take Dask's other side. So while Dask is, we use it to parallelize and distribute data frame operations, we can do the exact same thing with Dask arrays. And this is one of the things I really love about Dask is we can, just as easy we did the data frames, we can now do the arrays. And so we have 2 videos. And afterwards, when you grab the slides, you can check out the 2 videos of Dask doing both data frames and arrays. But I just want to give a quick, click through of what this speed up is like. So if I just have 2 terabytes of data and I want to do a summation of their arrays on a single core, just think of NumPy out of the box. It takes about 2 hours, 40 minutes. That's a single core. So then I'm going to parallelize that across all the cores on my machine. You get near linear speed up. It's about 11.5 minutes. On one GPU, this is the V100, that takes about 1 minute and 37 seconds. If I want to do that on 8 GPUs, it's about 19 seconds. And so that's the DGX1. It's a really high-end GPU server, all this NVLink and fully connected. We said, what if we did it on a set of servers with no NVLink and they're regular PCIe cards? So they're not with this fancy interconnect, and they're not the state-of-the-art high-end. They're just our little small $2,000 T4 GPU. It's a 75-watt one. It's a very low-powered GPU. And so with 16 of those across 4 machines, we did this in about 58 seconds, whereas doing it on 48 cores took about 11.5 minutes. And so even when you think about something, a GPU that's almost at cost parity or even cheaper than a CPU, you're still getting a massive improvement. And then we went crazy and we scaled it out to 3.2 petabytes, and we used 76 of the P100, so not the current generation. We went back 2 generations, mainly because they're cheaper. And we did it in about 54 minutes. So now some cuML. cuML is the machine learning part of our library. This is really where we talk about iteration and time saving and doing your kind of core data science things. How we build this library is actually really fun because it allows us to extend it very quickly. So we first start with CUDA, but we never write any of our algorithms directly to the CUDA layer. There's a bunch of CUDA libraries above CUDA, like Thrust and Cub and cuSolver, cuBLAS, Cutlass, NV, Graph, that have all these primitives, and they have things like gem operations. They template them out in very nice ways. So we never have to go all the way back down to the CUDA level and write out what a matrix multiplication operation should look like. And then we add on some other ML primitives. So different solvers that weren't there, distance calculations, and other things. And we use these as primitives. We don't write anything directly to the CUDA layer. We use these primitives. And then we figure out which ML algorithms need which primitives, and we stitch them together. And we build the algorithm. And then we use Python to bind that to a Python layer. And the beauty of this is, if we make a primitive faster, every algorithm that uses that primitive is now faster. So it really kind of reduces the overhead of the developer team to just use these primitives. And then also over time, we're going to use Python to bind to each of the primitives so that we can expose the primitives in Python. So if people just want to write their own arbitrary algorithms, while it might not be as fast as the optimized everything in C++ and then just binding it at a higher level, it'll still give really great performance without some of the, the difficulties of writing CUDA C++. And so we have a bunch of different functions and different ways of doing hyperparameter tuning and cross-validation, and there's a lot more to come. But I just want to give an example of what it looks like. So this is kind of doing clustering with dbscan. So we just, from cuML, import dbscan, dbscan.fit. It's the Scikit-Learn API. And so some of the speed ups, we're seeing somewhere between 10 to 20x on different algorithms once you get to a reasonable size. And a lot of people ask me, what's a reasonable size? For most GPUs, it's anywhere when you get north of about 2 gigabytes. If it's smaller than 2 gigabytes, you probably don't need a GPU for it. Use a CPU, you'll be fine. Once you get above 2 gigabytes, GPUs really start to take off, where the performance drastically exceeds the cost difference. And then especially in the cases with the T4, where it's cheaper than most CPUs in the server grade, it's really great to see this kind of 10x improvement at cost parity. In our last release, we also added a GPU version of Umap. So raise your hand if you've ever used TSNE. And raise your hand if you used Umap. OK, so one person. If you ever used TSNE, just try Umap. There's kind of this huge wave of people getting on this Umap boat. I've been a huge fan of Leland McKinney's. And I'm probably butchering his last name, but I'm really bad with names, so I apologize to Leland in advance. Umap is great. If you want to do dimensionality reduction, what Umap does is essentially the same as TSNE, but it comes from kind of a more rigorous mathematical background, so you don't lose some of the actual distance from some of the higher order dimensions as it compresses down. And so what you get is a faster dimensionality reduction that actually gives you better clustering. And then now we've GPU accelerated that. So the GPU version is about 15 times faster than the CPU version. Umap is about 15 times faster than TSNE. So if you went from dual socket TSNE on a server and you move to the GPU version of Umap, you're going to get over a 2 order of magnitude improvement and better clustering. And that's what I basically just consider magic. And so this is why we wanted to do this algorithm. And there's some really cool papers about using Umap with deep learning to figure out what's triggering in the different neural network layers to show similarities in why certain photos or pictures or images are classified in similar ways. And so some of the real applications of Umap are really exciting now that people can start doing this dimensionality reduction so much faster. And so when we started RAPIDS, when we launched back with 0.1, we basically had nothing. I always joke that we launched a little bit too early and it was painful. But one of the best things about open source is people are a lot nicer than you would think. And also, people have a lot more needs than you would think. And so it's great. Our issues just skyrocketed from the beginning. But we realized what people were using. So we fixed what people were using. We didn't really fix the things that people weren't. We added the features that people wanted. We didn't add features that people wanted. And here's where we are today. So we've added a bunch more single GPU algorithms. We have some multi-GPU, single node, and then we have a few multi-GPU, multi-node. And then from now to 0.9, we're going to complete out the single GPU algorithms, and we're going to have some more single node multi-GPU algorithms. But really what I'm excited for after 0.9 is we're going to really just make a huge push. We have been doing a lot of back-end development on communications and thinking about things like COCO that's used in a lot of the distributed logistic and linear regressions. We've been working with a lot of the networking and collectives teams. So we can really just make a big push into multi-node, multi-GPU algorithms. Because a lot of our early customers and users are saying, hey, single GPUs are great, but you were capped at about 48 gigabytes. Even in a single machine, most are not going to go buy a DGX2, which has 16 of the 32 gigabyte GPU, so half a terabyte. Most people have a machine that might have 100 to 200 gigabytes of GPU memory. They're basically saying, we need to go distributed. We need to go distributed now. And we've heard them loud and clear. So our big push is to have multi-node, multi-GPU random forests, K-means, KNN, and dbScan, in addition to the XGBoost that's been distributed for a while.
I guess these are all integrated with deep learning techniques as well?
Yes, so you can go from cuML, and you can literally just use DLPack to go to PyTorch, MXNet, or Chainer. The only one we don't have direct integration with is TensorFlow, and just go back to system memory as a NumPy array, and then back into TensorFlow if you want. And finally, cuGraph. So here are just some different data sets, a few tens of millions of nodes, hundreds of millions of nodes, a few billion edges. NetworkX, cuGraph. We see this 1,000x improvement. That's really exciting. But then I know what people are thinking. They're like, great, you're comparing it to a pure Python library. What about comparing it to something like GraphX? And so this is like one of the coolest things. I spent a lot of time in cybersecurity doing graph research. And so that it is, on a 4-node, 8-core cloud instance, it's 3,000 seconds. And then if you scale that out to 10 nodes, we're talking like 1,500 seconds. And that little blue line is 3 seconds. I probably should have used log scale, but I always think that log scale just doesn't look as good. So I stuck with just like a normal scale. GraphX, distributed, a single GPU. And so this is where we are today. Also using Dask. This is where we'll be by the end of the year. So we'll have multi-GPU. And so this is actually one of the few times where I'm like, buying a big machine makes sense. If you're doing graph, we have several customers who have 200 gigabyte graphs, and they're using GraphX. And to get page rank below an hour, they're spinning up 1,000 node clusters just to get it below an hour. With our multi-GPU techniques, we're basically trying to shoot for the 15 to 25 second range on a DGX2. So a single machine, yes, it's expensive, but you can manage a 1,000 node cluster and get things in an hour, or you can buy one machine and get things in sub-minute. And so I think this is when scale up really matters. It's for things like graph analytics, where just going distributed just kills all your performance. And so in closing, our goal is to get to 1.0 really quickly. We want to get to really hardened software that can be deployed. I love Matt Rockland, the creator of Dask, who's on our team. When someone asks him, can we use this in production today? He's like, what's your pain tolerance? Is it Spark 2013? Is it Spark 2014? Is it Spark 2015? Is it Spark 2016? Everyone has a different pain tolerance of what production is. We have some customers who have Rapids in production today, and they're saving, literally. There's a great article about one retailer who used Rapids for their perishable goods forecasting and saving over $100 million by just having better accurate models at a very granular store level detail. We have people using many different parts of Rapids in production today. And so when people ask me, is it production ready? My answer is always going to be, it depends. It's not 1.0. We probably won't get to 1.0 until early next year. That's actually, that's fine. We want to get the features and functionality, and we want to make sure that our APIs are stable before we officially hit that 1.0 stamp. And so on our way to 1.0, there are certain things that we care about. Speed is not one of them. It's fast. No matter what your metric of speed is, total cost, pure speed, Rapids is really fast. We can make it faster. We're not going to make it much faster. There's some things that we could do. There's some compression tricks. There's some better caching of kernels. We could statically compile more kernels. But this is really not our focus. Our focus is this, features. We want to get all the core features wrapped up as quickly as possible. We want to get the features that people care about for actual big data and scaling. And then we want to have a better user experience. We're following the Python APIs, which is a very good start. We replaced CFFI with Python, and that coming out this release, which is great because I complained to my dev team. Jiwei is from the team here, and he knows how much I complain about our CFFI. So that's great that we've done that. And now we just need to just continuously make sure that the user experience is just top notch. And those are the main things that I care about on our way to 1.0. Today, Rapids is integrated into Google Cloud, Azure, Databricks, Kubeflow, and if you're an Accenture customer, they have it in Accenture Insight Platforms. By the time we get to 1.0, we want to have native integration into every major cloud, both through containers and in virtual machine instances. And then we want to support every orchestration layer. So Slurm, Kubernetes, Yarn, fully, and make sure that that's easy and seamless for people to use. Back in 0.6, or sorry, prior to 0.6, people complained that our documentation was a little bit hard to understand and find. So we spent a lot of time with our UX team. We cleaned up our docs. We made them very pretty. They are aesthetically pleasing docs. Like, I like looking at my docs. That's just weird, I know, but they're pretty. It makes it really good for the end user. So please check out the docs, even if you never use the library, and just tell us if you don't think the docs are aesthetically pleasing, and we'll make them better. We also have some quick to get started guides. I pushed back on my product team a little bit on this, but we still did it anyway. It's very close to Pandas and Scikit-Learn. I think there's enough tutorials out there, but we still have some getting started quickly stuff. But at the end of the day, if you can use Pandas, you can use Rapids. So how do you get it? GitHub. You can grab the source code, conda install. You can pip install as of today. That may change. There's a really great talk going on at PyCon. I think we're going to take a stronger stance on pip and not be one of the offenders of breaking pip as badly as pip is being broken today. So pip is there today. It might not be there after 0.7. But I think as a community, we need to really come together, and pip packaging is really difficult. It's also available in NGC, the NVIDIA GPU Cloud, and they're doing some really amazing things with NGC. So please check out the NGC containers and everything, all the other containers out there that we have GPU acceleration of. And then we also have it on Docker Hub as well for people who are just huge Docker Hub fans. And join in. Open source is a team sport. We wouldn't be this far along without all the active users, all the issues, everyone giving conference talks. I got a tweet from Eric Ma, who's like, oh, I'm at PyCon, I did a NetworkX talk, and I plugged a cuGraph and showed an example. Adam was here earlier this week, and he was showing cuDF with Spark. If you ever want to give a talk or a tutorial, or talk to your internal teammates about Rapids, just join us on the Rapids Slack, ping me, let me know. Happy to help out with any material. Integrate into your products. We love feedback on what we're doing well. We love feedback on what we're not doing well. If you think something isn't documented well, despite my docs being really pretty, please make a PR for docs. Pull requests if you want to add some code or you want to add some functionality. And honestly, issues. We love issues. Issues are our lifeblood. If you have a problem with something, tell us about it. And then if you have some really cool GPU code, donate it. And that's it for me. So on the university side, NVIDIA does a lot of discounts on GPUs. And we also have a GPU grant program. It's somewhere on the NVIDIA.com website where people can say, hey, I want to do this research project. Here are the outcomes of it, blah, blah, blah. I would like a GPU to do this. And we have a submission for that every year. And then we partner with a lot of the major university computing centers. So you should be able to have GPU resources somewhere to spin something up and try it. There's something internal that I can't say publicly. Yes, there's a plan for Windows support. I can't give you a timeline on when it will come, but my earlier response, if you asked me that 3 months ago, would have been no. Now the answer is yes, but I don't know when.
Do you have a suggested database parent? I saw on Apache Arrow who linked it, but do you have a suggested or preferred one?
Not really. Pick your database of poison. At the end of the day, we assume that people mostly are doing their data science for some type of data lake, where they've pulled data from numerous databases, stored in Parquet or a bunch of CSVs or Orc, and they're going from there. That's why we spent time on those readers first. But if your database can send Arrow, or even something that is close to Arrow, or even something that can go into Arrow, PyArrow can ingest a bunch of things as well. And so we wanted to support as many open standards as possible so people could get data into Rapids as fast as possible, no matter what their path to Nirvana was.
Omnisci, you mentioned about it, and what are the relationships there?
Omnisci was an early contributor to GoAI, the GPU Open Analytics Initiative. They spent a lot of time working on their database. They actually can go from Omnisci and export directly to a GPU data frame, Arrow, on the GPU. So going from Omnisci directly into Rapids is probably one of the easiest database connections there is. We love the guys at Omnisci. Todd and all of them know them very well. So Omnisci is doing really great things with the GPU database. Yeah. All right. Thanks, everyone.